In a previous video we saw we need to create random matrices and column vectors for our neural network, and now I'm going to go over the shapes that those matrices and vectors need to have in order to make sense for the neural network we want to build. And so if you are familiar with matrix multiplication and you already understand these concepts of neural networks, the weight matrices and the bias vectors, and why and how they are used, feel free to skip this video. Otherwise, bear with me. And so let's go ahead and recall that our example neural network gets 3 inputs, which are measurements from an animal, and the point is the network is going to try and distinguish between a dog and a cat. That's the point of this example neural network. And so I went ahead and made a drawing of this section of the network right under here, and let me scroll down. And there it is. This is the section of the network I just mentioned, and there's an L here for left and an R here for right. And I numbered the neurons on the left, and I lettered the neurons on the right. And what is going on is, as I just showed you, 3 things are going in on the left. And those are the measurements of the animal and are encoded as a column vector in here. This is what goes into to neuron number 1, to neuron number 2, and to neuron number 3. And what we see is, in some magical way, we are going to have a vote with these confidence levels encoded here in the connections, which are going to get stored somehow in a matrix, and then there's this vote and something comes out. And what comes out here is defined by matrix multiplication. That's why there's a cross here. This is not a cross, it's a times. And this table over here, this thing that looks like a 6x3 table, is actually a matrix in which these connections are stored. Remember that these are confidence levels. For example, in black over here at the top, we have the confidence level between 1 and A, and that is stored in the upper left corner of this matrix. The confidence level between neuron 3 and A is stored in the upper right corner of the matrix. And that's how you store all these confidence levels in here, in different colors, in this matrix over here. And then the way it works is matrix multiplication just does the voting for us. Whatever comes into A, so whatever A needs to use to make its decision is going to be whatever neuron 1 says, and then modified by the confidence that A has in 1, whatever neuron 2 says, modified by the confidence that the neuron A has in neuron 2, and then we also take into account whatever neuron 3 says, and it is going to be weighted by the confidence that neuron A has in 3. I'm sorry, this is very confusing. I just keep confusing myself with all the letters and numbers. The point being, something goes in, and the fact that we stored our confidence levels in rows means we can perform matrix multiplication, and then in here we get an aggregated, let's say the aggregated opinion of the neurons on the left. Then what we need to do is to sum our own opinions. So this first step, this first step over here is to listen to whatever the neurons have to say, and the matrix multiplication here yields a column vector, which is intermediate. And then what we get is that intermediate vector. We are going to sum it to our bias, So our own opinions about the subject, and then we get another vector which has exactly the same shape. And so actually maybe I should change the name of these to intermediate out. Okay. And that's why and where matrix multiplication comes into play. I can understand if it's a bit confusing. The purpose of this video is not that you fully understand matrix multiplication. I have even barely defined it. I just said it's used and it works in a way that is useful. So please go ahead and read about matrix multiplication online and figure out how it really works. But just bear in mind that we are going to use a weight matrix here, and the shape of the weight matrix depends on the numbers on the left and depends on the letters of the neurons on the right. Then we take whatever goes in, we multiply those two together to get a column vector as an intermediate step, to which we then add our personal biases, which finally yields the output of the network, or at least this layer. So this vector right here with 6 numbers is exactly what comes out on this right hand side. And then the process is repeated. So 6 numbers come out in here, and then if we scroll up, those were these 6 numbers in the middle. So whatever comes out here, we need to do the same process in here to get the actual network outputs. And if we have a deeper network, there is a network with more layers, we would need to do this even more times, but always in the same fashion. There's always a matrix whose size depends on the neurons on the left and on the right, and then we just perform a matrix multiplication here, a vector addition, and then we take whatever came out as the input for the next step. That's basically it. And so we are going to implement this now in APL.